The Mariana Trench is nearly 7 miles deep. At its lowest point, the pressure reaches more than 1,000 times the atmospheric pressure at sea level, roughly 8 tons pressing down on every square inch of surface. The temperature sits just above freezing. No sunlight has ever reached it. Nothing about it should support complex life, generate oxygen, or behave in any way that surprises a scientist who has studied deep ocean conditions for 30 years. And yet NASA sent researchers there, not oceanographers on a marine biology trip, a space agency with instruments designed to detect the signatures of life in places where life has no business existing. They sent those instruments to the deepest point on Earth and pointed them at the seafloor. What came back has rewritten rules that the scientific community considered closed. Why a space agency went to the bottom of the ocean. Before getting into what was found, the question of why NASA was there in the first place needs an answer, because it is the detail that makes everything else in this story land differently. Jupiter has a moon called Europa. Saturn has a moon called Enceladus. Both of these moons have liquid oceans sitting beneath thick shells of ice. Europa's ocean is estimated to contain more liquid water than all of Earth's oceans combined. Enceladus has been directly observed venting water vapor from cracks in its icy surface, which means its ocean is actively interacting with its rocky seafloor right now. Scientists believe the seafloors of both moons may have hydrothermal activity, hot water mixing with rock in total darkness, generating chemical energy the way Earth's deep sea vents do. If that is true, and the conditions match what exists at the bottom of Earth's ocean, then there is a real possibility that something is alive in those dark oceans today. To prepare for eventual missions to Europa and Enceladus, NASA needed to understand exactly how life survives in the most extreme ocean environments on Earth. That is what sent them to the Mariana Trench and to similar deep ocean sites. The research program was called Subsea, Systematic Underwater Biogeochemical Science and Exploration Analog, a partnership between NASA, NOAA, and the Ocean Exploration Trust. The targets were underwater volcanoes and hydrothermal systems whose temperature, pressure, and chemical conditions most closely matched what instruments predict at the seafloor of Enceladus. The whole logic of the program was this: if you want to know what life detection instruments should be looking for on an ocean moon 400 million miles away, go to the most extreme ocean environment on Earth, study it in detail, and build your detection strategy around what you find there. Before we move on, if you're enjoying this analysis, please consider subscribing. It helps the channel tremendously. The deep ocean was not the subject, it was the rehearsal. And the rehearsal kept finding things that were not supposed to be there. The pressure that changes everything. To understand what makes the Mariana Trench specifically so difficult to study and so strange in its findings, the physical environment needs to land first. Challenger Deep, the deepest point in the trench, sits approximately 10,935 meters below sea level. That is nearly 7 miles straight down. If you placed Mount Everest at the bottom, its peak would still be more than a mile underwater. The pressure at that depth reaches 1,086 bar, or roughly 15,750 pounds per square inch. At that pressure, water itself behaves differently. It becomes about 5% more dense than at the surface. Calcium cannot exist in solid form, which means the bones of vertebrates would dissolve. The first explorers who descended to Challenger Deep in 1960, Jacques Piccard and United States Navy Lieutenant Don Walsh, saw a flatfish on the bottom. Scientists later debated whether it was actually a sea cucumber. The conditions were so far outside normal biological parameters that nothing seemed certain. Only 22 crewed descents and 7 uncrewed descents had reached that depth as of 2022. The trench stretches for about 2,550 kilometers across the western Pacific, nearly the distance from New York to Los Angeles. For a structure that size, the number of scientific missions that have produced data from its deepest regions can be counted in the dozens. The instrumentation needed to function at that depth is extraordinarily difficult to build and routinely fails. During one expedition, a lander imploded catastrophically from the pressure before returning any data. Equipment rated to extreme depths regularly comes back damaged or does not come back at all. Whatever the trench contains, most of it has never been directly observed. What has been observed keeps producing results that contradict what the models predicted would be down there. The bacteria that should not exist at that depth. In 2019, a research team published a study in the journal Microbiome after conducting the most detailed microbial analysis of the Mariana Trench attempted to that point. They collected water samples at multiple depths through the trench using submersible technology and analyzed the genetic material of the microbes present at each level. The expectation was straightforward. As you go deeper, pressure increases, nutrients thin out, and the microbial community simplifies. What they found at depths below 10,400 meters, within the deepest water of Challenger Deep itself, was the opposite of that. There was an abrupt, sharp increase in the concentration of hydrocarbon-degrading bacteria at that depth. Bacteria that eat oil and organic compounds. The proportion of these bacteria at that depth was the highest recorded in any natural environment anywhere on Earth, including oil spill sites, petroleum-contaminated soils, and hydrocarbon-rich coastal zones designed to produce exactly this kind of microbial response. The researchers described it directly as unexpected. Their own word for what they found was shocking. The question the data immediately raised was where the hydrocarbons were coming from. Some portion was traced to surface pollution sinking down into the trench over time, but isotopic analysis of the sediment at the bottom showed naturally occurring hydrocarbons whose carbon and hydrogen isotope signature pointed to a biological source inside the trench itself. Something at the very bottom of Challenger Deep was producing organic compounds that a dense community of specialized bacteria had evolved specifically to consume at concentrations higher than anywhere else on the planet. No mechanism at that depth was expected to produce hydrocarbons at that scale. The trench is not an oil field. There are no known subsurface petroleum reserves feeding into it. The identity of whatever is producing those compounds and the reason the bacterial community around them is so extraordinarily dense remain open questions that the 2019 paper flagged directly. The source of those naturally occurring hydrocarbons and the bacteria that depend on them are still the most concentrated community of hydrocarbon consumers ever documented on Earth. The oxygen that rocks produced without sunlight. Biology class teaches a rule that has not had a single exception in the history of science until very recently. Oxygen comes from photosynthesis, and photosynthesis requires sunlight. About half of every breath you take was produced by phytoplankton near the ocean surface. The rest came from plants on land. Both processes depend on light. Without light, the rule held, you cannot get free oxygen. Professor Andrew Sweetman at the Scottish Association for Marine Science first noticed something wrong with his measurements in 2013. He was running experiments at the abyssal seafloor of the Pacific Ocean, in a region called the Clarion-Clipperton Zone about 4,000 meters down, placing sealed chambers on the seafloor and measuring oxygen levels inside them over time. In environments with no sunlight and no photosynthesis, oxygen is consumed as organisms breathe. The readings inside his chambers should have gone down. They went up, significantly. Over 2 days of measurement, oxygen levels inside the chambers rose to more than 3 times the background concentration. He assumed instrument error. He had the equipment recalibrated. He ran the experiment again. The oxygen kept rising. He spent nearly a decade running variations of the same test. having different colleagues check his methodology before accepting what the numbers were saying. His team published in Nature Geoscience in 2024. The source turned out to be potato-sized lumps of rock called polymetallic nodules, dense in metals including manganese, cobalt, and nickel, that cover wide areas of the deep Pacific seafloor. These nodules carry a measurable electric charge on their surfaces, with voltages recorded up to 0.95 volts on a single nodule. The standard AA battery runs at 1.5 volts. These rocks were running at roughly 2/3 of that. The researchers hypothesized that this charge was sufficient to drive electrolysis of seawater, splitting water molecules into hydrogen and oxygen through a purely geological process, with no biology involved and no sunlight required. Sweetman said directly in his paper that scientists now need to revisit the most basic questions about where aerobic life could have begun on Earth. Researchers at Boston University made the connection to NASA's targets immediately. Europa and Enceladus have no sunlight reaching their subsurface oceans. But if metal-rich rocks on their seafloors are doing what the Clarion-Clipperton nodules appear to be doing on Earth's floor, oxygen could be accumulating in those dark oceans right now, ready to support life that nobody has looked for yet. The dark oxygen finding has since been disputed by other researchers who question whether electrolysis is the correct mechanism and whether instrument readings were affected by other variables. Nature Geoscience posted an editor's note in April 2026 stating that aspects of the paper are subject to concerns being reviewed. The debate is active and unresolved. The oxygen readings themselves have not been explained away. What produced them is still contested. That is what makes it significant. A decade of repeated measurements that nobody can fully account for is not nothing. The water disappearing into the planet. The Mariana Trench is a subduction zone. This is the location where the western Pacific Plate collides with and slides beneath the Mariana Plate, grinding downward into Earth's mantle at geological speed. Scientists understood the basic mechanics of this process. What they did not understand was how much water was going down with it. In 2018, a team from Washington University in St. Louis published a study in Nature based on a year-long seismic survey spanning the Mariana Trench. Using 19 ocean-bottom seismographs and 7 island-based instruments, they mapped the structure of the subducting plate in 3 dimensions by analyzing how seismic waves move through it. The results showed that the amount of water being dragged into Earth's interior through the Mariana Trench was roughly 3 times greater than previous estimates had calculated. Ocean water seeps into the crust along the fault lines where the plates collide and bend. Under the right pressure and temperature conditions, chemical reactions lock that water into the rock itself as hydrous minerals. The plate then carries it downward, deeper and deeper into the mantle, to depths where it eventually gets released under extreme heat and pressure as a supercritical fluid that rises and triggers volcanic eruptions hundreds of miles away at the Mariana Islands above. Scientists had known subduction zones moved water into Earth. They did not know how much. The seismic data revealed the hydration extended 24 kilometers below the plate boundary, far deeper than any previous measurement had documented. The lead researcher, Chen Kai, of Washington University, stated directly that the main source of uncertainty in previous calculations had been the water content of the subducting upper mantle, and that the new seismic data resolved that uncertainty with results 3 times larger than anyone had modeled. That water, locked into rock and pulled into the planet at the deepest trench on Earth, represents a piece of the global water cycle that had been significantly underestimated in every model built before this study. The implications run wide. Subduction zone earthquakes, which are among the most powerful on Earth, are partly driven by the behavior of that water at depth. The amount of water in the mantle affects how volcanoes behave. The long-term balance of water between Earth's surface and its interior determines what the planet looks like over hundreds of millions of years. Every one of those calculations just got revised by a factor of 3 because of what instruments placed at the bottom of the Mariana Trench heard during a year of listening to the Earth. Why NASA treats it like another planet. In 2019, during the Subsea program, NASA researchers operating off the coast of California and Oregon in the Gorda Ridge system discovered a previously unknown hydrothermal vent field. They named it the Apollo Vent Field in honor of the 50th anniversary of the moon landing. The name was intentional. The researchers described the field directly as a window into ocean systems that could exist on Enceladus and Europa. NASA's Jet Propulsion Laboratory, JPL, has run separate experiments simulating the chemical conditions at Earth's deep sea vents to understand what life-building reactions might occur. The JPL research demonstrated that amino acids, the building blocks of proteins, form spontaneously when the right chemicals mix under the pressure and temperature conditions found at hydrothermal vents. The explicit purpose of that research was to inform the interpretation of data from future Europa Clipper and Enceladus missions. The reason NASA cares what is happening at the bottom of the Mariana Trench is that the Mariana Trench is the closest analog available to the conditions those missions will encounter. The pressure, the darkness, the chemistry, the absence of sunlight, the interaction between seawater and rock at extreme depth, all of it mirrors what instruments on Europa Clipper will be trying to read from 390 million miles away. Every finding from the deep ocean changes the calibration for what to look for and what to expect when those instruments finally get there. What this adds up to: the hydrocarbon-degrading bacteria at Challenger Deep were published in a peer-reviewed journal in 2019. The seismic study showing 3 times more water entering Earth's mantle through the trench than previously estimated was published in Nature in 2018. The dark oxygen readings from the abyssal Pacific seafloor were published in Nature Geoscience in 2024. The Subsea program's connection between Earth's deep sea and the oceans of Europa and Enceladus is documented in NASA's own published research. None of this is speculation. None of it is fringe science. All of it came from serious researchers using calibrated instruments and publishing in peer-reviewed journals. What it adds up to is a location, the deepest point on Earth, that keeps producing results that do not fit the existing framework. Bacteria thriving in concentrations no other environment produces, eating compounds whose origin is still unexplained, rocks apparently splitting water into oxygen with no sunlight and no biology involved, ocean water disappearing into the planet at 3 times the volume scientists expected, and a space agency pointing instruments at all of it, not because it is interesting marine biology, but because they believe what is happening at the bottom of the Mariana Trench is the same thing that might be happening right now inside the moons of Jupiter and Saturn. The trench is 7 miles deep, and we have made 22 crewed descents into it in the entire history of human exploration. Less than 0.001% of the deep ocean floor has been visually observed. The Mariana Trench is the part of that 0.001% that keeps producing the most unsettling numbers. What the other 99.999% is doing, nobody knows. If this video gave you something, subscribing takes 3 seconds, and it helps us keep making content like this.